Okay, so let me share a screen here. I've got your first homework posted on the website and on the Canvas. It'll be due like in a little while, like September 4th, so it's a Wednesday. So let me say a couple of words about really exciting homework. Number one, so this, it seems sort of a moral imperative to address this issue. Give an example of a commutative ring necessarily without identity that does not have a maximal proper ideal. And that is to say, given any ideal that's properly contained in R, I can find a slightly bigger ideal that contains it that's properly contained in R. There's a number of ways to do this. There's lots of ways to skin that cat. Number two, let R be a commutative ring with identity. Let that funny n be the set of x and R such that x to the n is 0 for some n and n. These are the nilpotent elements you're probably familiar with. And Z is the collection of everything in R that is killed by some non-zero element of R. This is important. This is called the zero divisors. Show that n is an ideal of R. This is sometimes called the nil radical of R. Show that the set of zero divisors is not necessarily an ideal of R. And in C, give an example to show that part A may not hold if the commutative hypothesis is removed, right? So the nilpotents may not form an ideal in the non-commutative case. Number three, let R be a commutative ring without identity. We define the Jacobson radical. This is actually important in commutative algebra. It comes up in some other things, analysis in particular. The Jacobson radical to be the intersection of all the maximal ideals of R. Show that if X is is an element of the Jacobson radical of R, if and only if 1 plus R times X is a unit in R for every R in R. So this is a characterization. You live in every single maximal ideal if and only if 1 plus any multiple of U is always a unit. And so that's a good way to characterize the intersection of all maximal ideals. And there's a good way to characterize the intersection of all the prime ideals. Show that the nil radical is the intersection of all the prime ideals of R. And finally, number 4 takes 3b to the next step, I think. So let R be a commutative ring with identity, and let I and R be a proper ideal. We define the radical of I to be, sometimes it's written actually radical I, as every x in R such that a high enough power of x knocks it back down into I. This is called radical of the ideal. Show that the radical of the ideal is the intersection of all prime ideals that contain I. Now, there's a fairly easy way to do this if you you can reduce this to 3b. So that's kind of a hint for one way to perhaps do the problem. Okay, any questions on that? All right. Okay, so let's see. I guess we don't need this on, do we? Let's turn off the thing here. Yes.
Can you give us an example for a non-trivial Jacobson radical?
Well, define non-trivial. Can you tell me how to turn that off? We've got some quid pro quo. Okay. Right, so the easiest way to build one of those things is to look at a formal power series ring over a field in one variable. The ideal generated by X in the formal power series ring over a field is the only maximal ideal, right? And so if you look at the Jacobson radical of that, you'll get that big, huge maximal ideal, and that's it, right? And let's also point out the intersection of all the prime ideals is zero if R is an integral domain, right? Because if R is an integral domain, then zero will be a prime ideal. And so that'll be part of the intersection. And so you get some silliness. So the intersection of all the prime ideals is always sort of silly unless you have zero divisors in it. Okay. Other questions? All right, so let's kind of pick up where we left off from last time. Okay. Okay, so the last thing we talked about was this sort of dramatic example of a ring that had some maximal ideals that, you know, just really wasn't practical to be able to write them down. And the last thing that I gave you was this definition of what a division ring is. Let me give you another definition that I think most of you know anyway. But R, well, actually, we don't even need to be commuted right now in here. Element A and R is nilpotent if A to the n 0 for some n. Notice that by default, A, it's 0 is nilpotent, correct? An element Z and R is a zero divisor if there exists a non-zero X and R such that XZ is zero. Okay, so let me say a couple of things about terminology here. The terminology here for zero divisor, you can expand this. Of course, it's clear how to expand this to the non-commutative setting. When you go to the non-commutative setting with zero divisors, all of a sudden you have to talk about left zero divisors and right zero divisors. And just because something's a left zero divisor, and that's why I'm a restricted commutative here. And you also have to have a non-zero. So technically, if R is a ring of one, then 0 is a zero divisor. In fact, if R has any element other than 0, right? So this is, you know, you were asking about the zero ring last time. This would be problematic, right, for the definition of zero divisor here. But so I consider 0 to be a zero divisor in a ring with 1, because there's a non-zero element 1 that multiplies 0 and gives 0. There are some authors that don't consider 0 to be a zero divisor. We call these authors incorrect. There's lots of reasons why it should be a zero divisor. let me talk about ideals a little bit. Last time I defined what an ideal is. So ideals and types of ideals, if you will. Recall a non-empty subset of R is an ideal if for all x, y, and I, R and R, we have number one, x minus y is still an I. So this condition just means, hey, I'm an abelian subgroup. And two, Rx is an I. So it's got that vacuum cleaner property, sucks everything into it. Right. So this is what we call an ideal. As I mentioned last time, it's the analog for ring theorists of what a normal subgroup is to a group theorist. And we'll see, we can quotient by ideals later. So, this is an example. And by the way, when I use the word proper ideal, sometimes I'll say that I is proper if I is a strict subset of R, right? What do the ideals in Z look like? Okay. For n being any actual number of zero, I would agree that these are ideals, right? Because certainly what you have is you have NZ, right? That's certainly an abelian subgroup. Everybody agree with that? And it's certainly a vacuum cleaner because if I have anything in the form n times k and I multiply it by j, it's still a multiple of n, right? Okay, but here's the rub. Why is this list exhaustive? Or do you claim it's exhaustive?
Yes.
Right? And how do you know that?
Do GCD nonsense.
Some GCD hocus pocus. Well, right. We get lucky here. There's a slick way to do this. Every ideal in Z has to be a subgroup of Z, right? So it's got to be a subgroup out of the gates, right? What kind of group is Z? It's a cyclic group. And the only subgroups of the cyclic group are cyclic groups. And we know from group theory that that's an exhaustive list. That's it. Those are the only possibilities because those are the only subgroups of Z in the first place. And we luck out because they all suck, right? They all have the vacuum cleaner property, right? So this is an exhaustive list. And actually notice that each of these ideals are generated by a single thing. And we're going to talk about this later, but C is what we call principal ideal domain because all their ideals can be generated by a single element, in this case, the element N. Right. Definition. Speaking of generating sets for ideals, definition. Let I well, you bring one. I didn't pull up this here. So let S okay, so suppose I have some subset of my one. The ideal generated by S well, anybody want to take a stab at what this is?
Intersection of all ideals contained in that.
Okay, that's kind of the, yeah, I don't, that's further than I'm wrong. This is kind of a slick way to do this. The intersection of all ideals of R containing I. Now, that's really kind of a slick way to do this, right? So, thank you. Yes. That's really kind of a slick way to do this. So, of course, when I think generated, I'm gonna give you kind of a workaday approach to this as well. But here's kind of my first question. What is the, I did say any subset here. What's the ideal generated by the empty set?
Zero.
The zero ideal, right? Because it's the intersection of all ideals. Because every ideal as a set contains the empty set, so it's the intersection of all ideals. And any ring zero is zero is an ideal, and it's contained in everything. So it's the zero ideal. Agree with that? For me to really justify this definition here, I guess we should probably make one thing clear, and that is note if I sub j is a family of ideals of R, then so is intersection. Maybe I should justify that very quickly. Let's see this. Note first that is going to be an insert. Right, we know from group theory that if you intersect a bunch of subgroups, you get a subgroup, right? So we've got that. So basically this gives us the X minus Y property. Now all we got to do is make sure that this is a vacuum cleaner, right? Now, let Z be an intersection and R and R, then for all J, Z is in IJ, and so RZ is in IJ. So therefore, RZ is the intersection. And so that establishes that this intersection is actually an ideal, so this makes sense. All right. Now, here's kind of, this is all fancy and it's good, and for theoretical formulations, this is really the best way to think about it. But if you work for a living, like we all do mathematically, here's a sort of a computational way to think of it. First of all, if you're doing a proof where you need to write elements down, you need to get your hands dirty, you think of it this way. We'll throw out as being the empty set, because I know that the ideal generator of that is 0. So, you're right. S equals. So suppose that as the set, a typical element of is a form. It's a sum of, let's say, RK, AK, K, let's say this, RIK, how about that? K equals 1 to N, where, I sub K is in index 7. So in particular, what I mean is everything in this ideal generated by S, where it's a set, is a finite R linear combination of elements of that set, which shows you why I threw the empty set out of this.
Why?
What's that now?
Why are you throwing the empty set out?
Well, because otherwise I would
Empty
have to.
sums are 0.
Okay,
So it should be precisely the same, and you just 0, right?
yes, but you're forgetting that I have a pea-sized little brain, and I don't want to write down that to just say you're correct. So, a typical element, and you can also see, of course, that this is an ideal directly, right? Because what happens if you take an element that looks like this, and another typical element looks like this? And you add this together, you'll get a bigger sum, right? And notice if you multiply R, the element of R, times this, it just factors through this. So this is an ideal, right? And it coincides with this. Everybody okay with that? Now, so here is well, let me get this. And I'm going to do this example here, and I'm probably going to regret it, but I'm going to do it to kind of show you sort of the magic of commutativity and especially of identity. Let's suppose R is ring, and that's, kind of it, right? And let's suppose S is what does a typical element of the ideal derived by S look like? I mean, certainly you should cover these things, but there's some other problems. Maybe it might be good to sort of consider what types. Well, so let A be an S. Right? And when I say ideal here, so my ring may not be commutative. I do mean an ideal. It's two-sided. Right? So multiplying, it's got the vacuum cleaner from both the left and the right. Well, let me kind of get the ball rolling. You get elements that look like this. Right? You get elements that look like this. There's also another form you get. Right? Because any ideal that contains S, if it's going to be a vacuum cleaner from both sides, it's got to contain RA, it's got to contain AR, and this isn't really good enough to guarantee that you have R1AR, right? And there's also another problem. Anybody see what the other problem might be?
What the identity sound,
What's that?
it has to do with the identity, but I can't remember what it is.
Yeah, that's right. So this is sort of the failure of commutativity right here, right? But there's also the identity. Can anybody put their finger on what missing the identity is gonna do for you?
A might not necessarily be in, like,
Well, so here's something else that might be in here. That has to be in the ideal, doesn't it? But if there's no one, you may not be covered in these cases, right? There may be no two in the ring. Right? So actually, what you have to do is, you also have to include NA or in the natural numbers. Okay. So what does a typical element look like? Well, it would be linear combinations of these things, and I think I've got it all. See, I've got to have it from the right, or from the left, from the right, from both sides, and then I have to have this. So in particular, so if R is not commutative and doesn't have one, then the ideal generated by A, right? So the smallest ideal that contains A has to have a set of elements the form. Actually, I guess I should actually, I'm going to expand this to Z, right? Because of course I have to have negative A here to be in the ideal as well, because this is so. So a typical element would look like NA plus RA plus AR prime plus TA prime. That's what a typical element would look like with N and Z, R prime, T prime, and R. notice that this does form an ability group, because when you add two elements of this form, you can just factor out the stuff on the left, stuff on the right. And here you're gonna just have a sum of things that look like this, right, which is fine. Actually, the principal ideal. So these will sum up, and these won't, so I guess I really should write it this way, shouldn't I? Ti a ti prime. Because there's no guarantee really that I can factor these out. So this is a complicated mess. Yeah, if R is commutative with 1, then the ideal generated by A is just a set of elements of R A, R and R. Much easier to wrap yourself around. So 1 takes care of this, absorbing this can turn around, and this can come out the front, and it's all in one thing. But see, even a ideal generated by 1 element, if you don't have an identity and you're not commutative, it can be more complicated than I think that you would really like to encounter. Okay, any questions on that? Okay, so let me give you all some definitions. I think that maybe you might be familiar with some or most of them. Definition. Let I and R be here again, we're assuming that that I is that R is commutative with identity. Number 1. If A, B, and I implies A is an I or B is an I, here A, B are an R, then I is prime. How many of you have seen that definition of prime ideal before? There's actually, the more general case is, so let me write this just kind of for your own interest. You have to do this in the non-commutative case, but more general definition is if the ideal P contains the product of two ideals A and B, then P contains A or P contains B. But in our situation, this element-wise easier one is perfectly fine. If I is a proper ideal, what this means is if you have a proper ideal, and I didn't say that here, but I want it to be proper for prime too, because otherwise, if I don't put proper, then technically the entire ring, which is an improper ideal, would satisfy the hypothesis of being prime and maximal. I want that. So I want this to be proper here. If I is proper, and you can't shove another ideal between I and R, right? So if you have an intermediate ideal between I and R, it's either got to be I itself or the whole ring, then we say I is a maximal ideal. actually, let me go back and correct this here. Let me just say right here, we'll say at the outset that for this definition, my ideas are proper. If A is an R and A to the N is an I implies A is an I. For all A and R, A to the N is I, implies A is an I. Then we say I is, anybody know this stripe? This one's radical. By the way, a quick observation shows that if you have a prime ideal, it must be radical. Yeah, R. If A, B, then I, and A is not an I, we say, anybody know what this one is? So if you have a product of two things in I, and one of the elements of the product is not in I, then that implies that the other one too is sufficiently high power as an I. If the ideal has that property, anybody know what it's called? This is primary. I'm gonna look at the integers with this in a moment, and then see where the definitions come from. And finally, if there exists X and I such that I is the ideal generated by X, then I is principal. Note, we have seen all ideals in Z are principal. Right. Let's take Z apart. Let's. Let's know what the maximal ideals look like. Not completely.
All zero.
There. Maximal ideals are the form P, where P the non-zero prime. So the ideal generated by 2, the ideal generated by 3, the ideal generated by 8, 6, 7, 5, 3, 0, 9. These are all maximal ideals. It's fairly easy to see, isn't it? Because if you have so the integers is generated by 1, it's maximal ideal, or we hope it's maximal generated by P. If you have something that generates this, then K must divide P. But the only divisors of P are itself and 1, right? How about the prime ideals? In this case, right, it is set maximal ideals union the zero ideal. So that's wrapped up in a neat package there. Okay, how about this? What do the radical ideals look like? Want to take a stab at that? I think you got it reversed. Characterize what it, so well, let's think about this for a minute then. Like suppose. So much better. You might tell me. So here's what I know. I know that. So, of course, any ideal in Z is principal, so there's no alternate I will be writing this out. And I'm gonna take advantage of a little bit of, fundamental theorem arithmetic here. I know that I can factor this as, that's probably the worst case. So let's suppose that I factor A down into its prime powers, right? Where each of these BI's is at least one, otherwise I wouldn't put it in. Now, this thing needs to have the property that if a power of this is divisible by this, then the original element had to be divisible by this. Does anybody see what criteria you need? What's that?
Square free.
That's it. So. You can't, it has to be square root. You can't have any power that exceeds one, right? Notice, if you think about it, if that means there's a big enough power of this, it's divisible by all these, right? But these are prime elements. That means that they all had to divide X in the first place, right? Because they're distinct, right? So if you're of this form, it has to be a radical ideal. And on the other hand, what happens if, for example, can you think of something that's not in there, but a power of it is? There you go. There you go, right? If you square this thing, it's divisible by this, right? But this thing is not in that ideal because the power here is okay. So here's what the radical ideals look like. P1, P2, so P with PI distinct primes. And if some of you like the number theory terminology, Eric put it most succinctly just by saying it's generally by some square frame and not one. How about primary? Right, right. Primary ideals are ones that are generated by So I do this example because it illustrates, I think, what these concepts are doing. Basically, radical ideals, if you notice, are intersections of prime ideals. Right? And actually, we're going to see that really goes across the board, right? That extends from Z well. Primary didn't extend quite as well, but primaries ideals are sort of like prime powers. Now, that's very fast to notice because there are some pretty, it's easy to have exceptions to this, but this is sort of the spirit of them in a certain sense. Okay, any questions on that? Okay, so I'm going to give you kind of one last little thing here. I meant to bring up earlier. So now we've seen these ideals, you might think, you might ask yourself, see if you can find polynomials that we can't disregard. Actually, in a certain sense, this is no different than Z, because this is also a principal ideal domain. If you want to challenge yourself further, do this in two variables. Right? See if you can figure out what the maximal ideals look like and so forth. Okay, let me give you a theorem here. And by the way, this theorem could be a little bit more general, but I'm going to just do it here. If R is a finite ring, then every element of R is a zero divisor or a unit. And I can't remember off the top of my head if I used this terminology before, but a unit is an invertible element, like in a division. It's just something that has multiple divisors. And here's the interesting part of this is, notice I didn't even say it's a ring with identity, because here's the rub. If you have a ring without identity and it's finite, every element's a zero divisor. If you have even one element that is not a zero divisor, you have to have an identity. It forces the identity condition. And that's kind of interesting. Now, I find this is an interesting theorem in the following sense. In a finite ring, any element of R is either a zero divisor or it's a unit. This is far from true in most rings that you encounter in real life, right? So think about it this way. Think of the integers. What are the zero divisors in the integers? Zero only, right? What are the units? What are the invertible integers? 1 and -1, right? Everything else is neither a unit nor is it a zero divisor, right? But in a finite ring, it's all one or the other. So how would you do this? Well, any ideas on how to do this? So I'll let you all think about this tomorrow. Let me give you a hint to start this off. Pick a non-zero element of A. And look at the sequence of elements all in the ring. Now, by hypothesis, this ring is finite, right? So what must be true about this sequence of powers of A? There must be a repeat. So at some point, you have to have AM equals A to the M plus A. And that might get your truck started. So see if you can figure out why this theorem is true. Okay, questions? All All right, well, you all have just a fabulous week, and we will see you on Monday.